Hello everyone, welcome to the Discrete Maths lecture series. We have started the principle of mathematical induction, and then in this lecture I'll be doing two more examples of a little different kind using principle of mathematical induction, and then we'll discuss the principle of strong induction. So look at this example. So using this mathematical induction formula, induction technique, we can also use we can also prove that this kind of inequality. It says that you have to prove that 2 to the power n is less than n factorial for every integer n with n greater or equal to 4. Right. So you assume that suppose Pn is such that 2 to the power n is less than n factorial. We have to prove this one. Now you verify that for n equal to 1, 2 and 3 this inequality does not hold. Because if n equal to 1, 2 is not less than n 1 factorial. 2 to the power 2. So 4 is not less than 2 factorial, which is 2. Similarly, 2 to the power 3, which is 8, is not less than 3 factorial, which is 6. But the basic step is like basic step, you have 2 to the power 4, which is 16, which is definitely less than 24, which is equal to 4 factorial. And therefore, your basic step is P4, which is true. P4 is true in this case. Now, what is your next job? Because you are going to use the principle of mathematical induction, you have to prove that the inductive step. So, what is the inductive step? What is the inductive step? So, you assume that Pk is true. So, assume Pk is true. But what is this k? K should be greater or equal to, because your base case is 4, so k should be greater or equal to 4. For some k which is greater or equal to 4. Right? So you assume that pk is true. So therefore, what is pk? Therefore, I can have 2 to the power k must be less than k factorial. 2 to the power k is less than k factorial. So this you write it as equation number 1. Now with the help of this pk, you have to prove that pk plus 1 is also true. Now how do you prove that pk plus 1 is also true? So take this expression 2 to the power k plus 1. You have to prove that this is less than k plus 1 factorial. But how to prove? You have to take the help of pk. So to do that, this I can write it as 2 into 2 to the power k. But 2 to the power k is less than k factorial. I can use this fact. So this is equal to 2 into k factorial. But I need to have this expression as k plus 1. So if I have 2 is replaced by k plus 1, then only I can able to write that 2 power k plus 1 is less than k plus 1 factorial. But see that k is greater or equal to 4, right? So 2 must be less than k plus 1. So therefore, this is less than k plus 1 into k factorial. But k plus 1 into k factorial is what? It is k plus 1 factorial. So therefore, what you got? 2 power k plus 1 is less than k plus 1 factorial. Therefore, your pk plus 1 is true. But whenever your pk is true, because you have proved it using pk, whenever your pk is true. So your pk imply pk plus 1. Hence, by principle of mathematical induction, we have Pn is true for all integer. So because that your basis case is from 4 onwards, so for all integer n greater or equal to 4, our proof is done. Right? So in this way, we can use principle of mathematical induction to prove some inequality as well. So this is the formal proof of it. You can look into it. I have one more example. Again, it is a little bit different kind, that use principle of mathematical induction to prove that n cube minus n is divisible by 3 when n is a positive integer. Because you have to prove that statement of the form Pn for all positive integers, so you can use the mathematical induction if it is useful at all. So how to prove that? So assume that Pn is the statement such that n cube minus n is divisible by 3. n cube minus n is divisible by 3. So what is your base case? Your base case n is a positive integer, right? So base case, the n positive integer starts from 1. So base case, best case should be p of 1. Now what is p of 1? P of 1 is true or not? Yes, 1 cube minus 1 is 0, which is divisible by 3. So therefore pn is true. So as 1 cube minus 1 is equal to 0 is divisible by 3. So p of 1 is true. Base case is done. Now inductive step. Inductive step is assume that pk is true. So assume that pk is true. Now what is pk? pk is nk cube minus k is divisible by 3. Right? So pk is true means, but some integer is divisible by 3 means what? It is a multiple of 3. Right? So k cube minus k, it is divisible by 3. Therefore k cube minus k is a multiple of 3. So 3 into some integer m, where m belong to z, set of all integer. So some integer. So it is a multiple of m. Now what you have to prove? That pk plus 1 is true. Pk plus 1 means what? K plus 1 whole cube minus k plus 1 is divisible by 3. That means k plus 1 whole cube minus k plus 1 is a multiple of 3 we have to prove. Right? So to prove that, now we will take the expression, left hand side expression. So k plus 1 whole cube minus of k plus 1. It is equal to k cube plus 3k square plus 3k plus k minus k minus 1. This is equal to, we have to prove that this expression is in the form of multiple of 3. So we can always take the help of pk. So this expression will take the help. So now I'll just rearrange k cube minus k plus k cube minus k I have taken, and then I will take, okay, sorry, here I have written a little mistake. I have to do, this is actually 1, right? And so this 1 and minus 1 will be cancelled out, and I have taken k cube minus k one side, and then after that I'm taking the rest of the element, 3k square plus 3k. But this has some value which is 3 into m by pk. So this expression I have taken the help of the plus 3k square plus 3k. So which I can write here as 3 into m star. What is that m star? Where m star is equal to another integer m plus k square plus k, which is belong to z. Therefore, this expression is a product of 3 into some integer. That means it is a multiple of 3. Therefore, this expression is divisible by 3. But what is this expression? This is pk plus 1 then. If it is divisible by 3, therefore, pk plus 1 is true. But how you have proved that? You have proved that with the help of pk. Whenever pk is true. So our proof is done. Hence, by principle of mathematical induction, we have Pn is true for all positive integer n. Pn is true for all positive integer n. Proof is done. Right? So these two problems I thought to discuss before discussing the strong induction method. I hope this is clear. Now we have few homework type problems. So all of you check this problem. This one again we have already done. This is a particular case. You should able to do it. Then again another inequality. Again you should able to do it. This problem is bit tricky, but this one also you can do. You can also look at the book. This is a book solved problem, right? So you take them as a homework. Now I will discuss about the strong induction method. Now this strong induction is almost similar to the principle of mathematical induction with a little change. Like suppose we will consider the same infinite ladder, and this one was the steps. These are the steps. Now here you have two capability. One is you should able to reach the first step or the basic step, and if you are up to kth step, that if you have 1 2 3 4 up to k, if you can go to one more step, right? If you are up to k step, you can able to go one more step. So these two property, if you have this two capability, then you will say that you can able to reach the whole ladder, whole infinite ladder. How? Because you said that you can able to reach the first step. Then if you apply this technique, so you can able to go to the, because you are up to 1, so you can go to the level 2, step 2. Then you are up to step 2, you can able to go to the step 3, then step 4. Like that you can able to reach the, this condition will imply that you can able to reach the whole, write the whole infinite ladder. Right? So this is the principle of strong induction. So what is the difference between this one and principle of mathematical induction? During that time we discussed that if you are exactly at kth step, then you should able to go to the k plus 1 step, right? So pk imply pk plus 1 in this previous case, principle of mathematical induction. But we are discussing strong induction is that basic step is same, that you should able to have the p1 is true, and if you are up to kth step, you should able to go to the k plus 1. That means up to k means what? That p1, p2, like all of them, and dot 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 up to pk, all of them true imply that pk plus 1 is true. So this two capability, one is your p1 is true, and this up to pk all true imply pk plus 1 is true. These two capability if you have, you will say that the pn is true for all positive integer n, right? So basic step you have to identify depending on the problem. And then what is the principle of strong induction? The similar kind of thing. To prove that Pn is true for all positive integer n, where Pn is a propositional function, we complete two steps. One is basic step, P1 is true, and then the inductive step, that P1, P2, P3 up to Pk, all will imply Pk plus 1 is true. Right? So that's what we discuss. Now, if you do one example, we'll understand the significance of this method. So that if n is an integer greater than 1, then n can be written as the product of prime. Now this proof we can do it as a using the strong induction technique. Right? How to do that? So we'll assume that let Pn be the statement such that Pn is such that n can be written as, n can be written as the product of prime. Product of primes. So this is our statement Pn. Now can you tell me that where n must be greater than 1? Right? N is an integer greater than 1. Now can you tell me what is my basic step? So your basic step, like you have to prove that n is an integer greater than 1. So what is the first integer greater than 1? 2. So your basic step is 2. So base case, what is your basic step or base case? P of 2. But whether P of 2 is true or not? P of 2 means 2 can be written as the product of prime. Yes, because 2 is itself a prime number, right? So it is a product of 1 prime, right? So therefore, P of 2 is true. P of 2 is true. Why? Because 2 can be written as a product of 1 prime. So P of 2 is true. So I have not written, and in the formal proof it will also be written. So I am doing little shortly. So inductive step is what? IS, inductive step. Now you will have to apply the strong induction method, right? So here the technique is inductive step is P1, it's like P2, P3, P2 up to Pk, all should imply Pk plus 1, right? So what you have to assume that, so up to K all are true, we have to assume. So assume that your Pj is true for 2 less or equal to j less or equal to k. So up to k all are true for some integer k greater than 2. Right, so P2, P3, P4 up to Pk all are true. That's what our assumption. You have to prove that Pk plus 1 is also true. Right, now what is Pk plus 1? Pk plus 1 means you have to prove that k plus 1 can be written as the product of prime. Where your assumption is P2 can be written as product of prime, 3 can be written as product of prime, dot 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 up to k all integers can be written as product of prime. This is your assumption. You have it already. You have to prove that k plus 1 is also written as product of prime. Now k plus 1 is an integer, right? So it can be either, now k plus 1 is an integer, so k plus 1 is either prime or composite. or composite. So case 1, if your k plus 1 is prime number. So k plus 1 is prime. If k plus 1 is prime. Now if your k plus 1 is prime, then k plus 1 is already a written as a product of 1 prime, right? So in this case, pk plus 1 is true. Then pk plus 1 is automatically true. Correct? Next, if k plus 1 is composite. If k plus 1 is composite. Now composite means what? Composite means it should have some factor other than 1 and the number itself. Correct? Now other than 1 and the number itself means what? It should be between 2 to k. Right? So if some integer is composite, so we can always write that k plus 1 can be written in the product of some integers a and b. Where will that this a and b can be 1 or k plus 1? No, because we are taking composite number, we have to take some different factor which are other than 1 and k plus 1 itself. So this a and b should be lies between 2 to k. So where 2 less or equal to a less than k up to k. Right? So this a and b, because it's a composite number, we have taken that factor which are between 1 and k plus 1, but not 1 and k plus 1. So k plus 1 is you have written in the form of a into b. But what about a? A is some integer lies between 2 and k. What is your assumption? Your assumption Pj is true for all integer between 2 to k. A is falling under them. Therefore, P of A is true by our assumption. Right? So P of A, like that means by induction hypothesis, A can be written as a product of prime. At the same way, B can be written as a product of prime by our assumption. Right? So A is a product of prime. Maybe I'm writing as product primes are P1, P2, Pa. Some integer maybe PR. Similarly, B can be written as a product of prime, right? So B can be written as product of prime, which is Q1 into Q2 into dot dot into Q maybe S. Because A and B are lies between 2 to K. So by our assumption, P of A and P of B both are true. Therefore, A can be written as product of prime, B can be written as product of prime. And at the same way, K plus 1 can be written as product of prime because this is the product of A and B. So P1 into P2 dot 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 PR into Q1 into Q2 dot 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 QS. Right? And hence K plus 1 can be written as product of prime, and therefore what is that? That means pk plus 1 is true. But how you have proved that? You have taken the help of this statement. What is that? You assume that up to pk all are true, right? So what we got basically, therefore p2 and p3 and up to pk plus 1, sorry, pk all together imply that pk plus 1 is true. So this is your inductive step. You have already proved the basic step P2. Hence, by principle of strong induction, we can prove that, like we have proved that Pn is true for all positive integer greater than 1. Our proof is done. Now you see that in this case, the principle of induction technique will not work, right? You have to use the principle of strong induction. Otherwise, you cannot say that one of them can be written as, like both of them can be written as product of prime. So if it is only true for k. So up to k all are true, only you can prove this one. Right? So this is the uses of principle of strong induction. So look at this. This is the formal proof that everything is written explicitly. You can look into this one as well. Now, I will discuss one more thing, which is something, but like I'll first give you some example, and then you can we can tell me. Like, look at some observation. I'll give some sets. S is equal to 2, 4, 6, 8, and 10. S2 is equal to 0, 3, 9, 27, and something, and so on. Then I am taking S3 is equal to some integer maybe. Okay, this set is up to finite only. Let us take. Right, so I have taken it a finite set. And then I will take some infinite set, maybe 0, 1, 2, 3, and so on. And I have taken another set as -2, -1, or okay, just a second, not -1, -2. I'll take another set which is -4, -2, 0, 2, 4, dot, dot. So I have taken 4 sets. Can you tell me that what is the least element for the set S1? Least element for the set 1, S1. Yes, the least element for the set S1 is, least element for the set S1 is 2. What about S2? What is the least element for the set S2? The least element for the set S2 is 0. Least element for the set S3 is what? Although it is an infinite set, but the least element for the set S3 is, it is 0 again in this case. But what is the least element of the set S4? Can you define? Can you find out? You may say that -10 lakh to the power -10 lakh, -10 lakh to the power 10 lakh. But I can say -10 lakh 1 to the power 10 lakh. So least element is not at all defined in the case of S4. You cannot find the least element, right? So least element does not exist, does not exist. You cannot get. So here you observe that in all the cases, okay, what is the least element for this set? There is no least element, right? Because there is no element even. So least element, it does not exist in this case also, right? So what you observe, if the set is non-empty because it has some element and positive, then you cannot get a least element. Here also, set is non-empty and elements are positive, non-negative, you can have a least element. Although it is an infinite set, but non-empty set and elements are non-negative, you have a least element. But this one, non-empty, but elements are includes negative number as well. So in this case, it may not, but you cannot give guarantee. So in this case, it list element does not exist. In this case, it is an empty set, list element does not exist, right? So from this, we got some idea called the well ordering principle, well ordering property. What it says, every non-empty set of non-negative integers has a list element. Every non-empty set of non-negative integers has a list element. Non-negative, non-empty set of, yes, non-empty, it should be non-empty, it should be non-empty. So this one non-empty does not have non-negative set of non-negative integers. If you have this, you can always give guarantee that it will have a list element. So because this well ordering property is there in the syllabus and the statement is only there, I hope you understand the statement, right? Now the significance of this theorem is, like, you can prove the division algorithm that we'll discuss in our number theory, elementary number theory portion, using this well ordering property, right? So this division algorithm is very significant in theorem, but that kind of theorem we can prove it by this very easy statement that every non-empty set of non-negative integers has a list element. That is, which is very easy to understand this statement. So even the statement is very easy, but you can able to prove a very significant theorem with the help of this, right? So the theorem proof is not there in the syllabus, but still I have kept it in the slides. If you are interested, you can go through that, but at least you should understand the meaning of the well ordering property and you should able to apply that, right? So this is the theorem. So I am done with my lecture. All the content I have taken from this book only, right? So thank you very much. we'll come up with the in the next video with a new unit. Thank you. We'll meet in the next video.